We're now going to discuss the mean pressure of an ideal gas. Actually, we will be deriving the ideal gas law. We call F the force exerted by one molecule on the right wall of a container. So let's say that we have a container that has dimensions Lx, Ly, and Z is coming out. So there's Lz also. And we have this container filled with an ideal gas. And as I said, F is the force that is exerted by a single molecule in positive x direction. And this is basically acting on the right wall of this container. As you can see here, it's on the right wall. Now F sub r is the same force when the molecule is in state R with energy epsilon r. So epsilon r, F sub r is once again the force, the value of F when the molecule is in state R with energy epsilon r. Okay? And as a result of this force, let's think about what is going on here on this right wall. We're going to see that this wall will be displaced by a small amount, or let's imagine that it will be displaced by a small amount. So I have the wall moving to its new location here, basically displaced by an amount dlx. Okay, so the molecule, the force exerted by the molecule is going to do some work. It will displace the wall to its new location at Lx plus dlx. All right, so let's imagine that the right wall is displaced by an amount dlx. Okay, now what is the work done by this force? Work done by the force Fr when the molecule is in state R is the dot product of the force with the displacement dlx. So let's remember, work is the dot product for a constant force, dot product with the displacement delta x. So the force is in I hat direction, and I have the displacement in the I hat direction. So the dot product gives me Fr dlx, and this is going to affect the energy of this gas in what way? Well, we have the first law of thermodynamics, which says that the change in the energy of the gas, dE, will be equal to the heat added to the gas plus the work done on the gas. So this is work being done by the gas. So in this case, I see that the d epsilon r will be equal to dW, which is once again work done on the gas, but this is work done by the gas. Therefore, this dot product, the work done by the gas, will result in a decrease in the energy of the molecule. All right, so because this is work done by the gas molecule, so it results in a decrease in its energy. Therefore, you can see that this equation implies the force exerted by a single molecule on the right wall is minus the derivative of its energy with respect to displacements in the positive x direction, and here Ly and Lz are constants. All right, so the displacement is only to the right. Then basically, having found this relationship between the force that is being exerted by the gas molecule and the change in its energy, we can calculate the mean force. Then we can calculate the mean force once again still exerted by one molecule. This is going to be, by statistical definition, F bar is sum over all possible states, probability of having a state R multiplied by the corresponding force. So this will be sum over all possible states, Boltzmann factor e to the beta epsilon R, multiplied by the force, where the force is minus del epsilon R del Lx, divided by the partition function sum over R e to the minus beta epsilon R. Now, if you take the derivative of e to the minus beta epsilon R, Boltzmann factor, with respect to Lx, so let's try that. If I have the derivative of the Boltzmann factor e to the minus beta epsilon R with respect to Lx, this would be the derivative with respect to energy of the Boltzmann factor multiplied by the derivative of the energy with respect to changes in Lx. So the derivative with respect to energy will just give me minus beta times the Boltzmann factor e to the minus beta epsilon R. Then here I have the derivative of the energy with respect to Lx. So I'm going to get minus beta, the Boltzmann factor e to the minus beta epsilon R del ER del Lx. This is basically equal to the derivative of e to the minus beta epsilon R. So what I have here is the Boltzmann factor multiplied by minus the derivative of epsilon R with respect to Lx. So let me find out what that should be. So I'm going to get minus the derivative, minus the Boltzmann factor e to the minus beta epsilon R del ER del Lx, which is what I see in the numerator here, sum over R, this factor. This is equal to minus 1 over beta so the minus beta on the left hand side goes to the right hand side as minus 1 over beta, because I have another minus sign here. So this is actually going to be plus. So I'm isolating minus e to the minus beta er multiplied by the derivative with respect to Lx of the energy. So this is plus 1 over beta ddlx, the Boltzmann factor, e to the minus beta epsilon r. So we're going to get, therefore, we would have for the force, the mean force exerted by one molecule, 1 over beta derivative sum over r, derivative of the Boltzmann factor with respect to Lx divided by the partition function z, because I can take the derivative outside of the summation. F bar is 1 over beta d dlx sum over r e to the minus beta er divided by the partition function, and this will be equal to 1 over beta 1 over z del z del lx. So we find that the mean force exerted by one molecule is then 1 over beta derivative of natural logarithm of partition function with respect to Lx. So once again we can calculate the mean force exerted by one molecule just by calculating the partition function. But we have already calculated the partition function in the previous discussion. So what was the partition function? Partition function was natural logarithm of the partition function was here natural log v plus 3 ln b minus 3 over 2 ln beta. So if I use that for the partition function, so if I recall, the natural logarithm of the partition function was natural logarithm of v minus 3 over 2 natural logarithm of beta plus 3 natural logarithm of b, where v is lx, ly, lz, and b was a constant. I can find the mean force to be 1 over beta. If I take a derivative of the right hand side with respect to Lx, Lx only appears in the volume, del ln v del Lx. So this would be 1 over beta, 1 over the volume, del v del Lx, and this would be 1 over beta, 1 over Lx, ly, lz, multiplied by ly, lz. Because I have Lx, ly, lz, the derivative will give me ly, lz. So these ly, lz's would disappear. Then I would find that the mean force exerted by a single molecule is kT divided by Lx. Now, if I were to do the same thing for a polyatomic gas, so let me remind you, for a polyatomic gas, in the energy term here, I would have for the force minus ddlx, the translational kinetic energy, plus rotations and vibrations which are with respect to center of mass, therefore no dimension dependence, they don't depend on the dimensions of the box. So this would be the same thing, del epsilon r, kinetic term del Lx. So the result that I would obtain here would be the same. So that is, since the intramolecular energy, not the energy between molecules, it's the molecule energy inside the molecule, intramolecular energy, that is due to vibrations and rotations, is independent of Lx because it is due to, with respect to the center of mass, the same conclusion is valid even if the gas is polyatomic. All right. Now, if I extend this discussion for the total force, the total force that I will see exerted by the gas molecules on the right hand side will be the sum over all molecules, I equals 1 to n, their corresponding forces. So if you take the average value of this force, total force, you would get I equals 1 to n f sub I average value, and this will be equal to just the number of molecules n times the mean force per molecule. So n, I have n molecules, and therefore for the total force mean value I can write n kT divided by Lx. So because the mean force per molecule was kT divided by Lx. Now if I calculate the mean pressure, that is the mean force that I'm applying per area, perpendicular area. Perpendicular area in this case will be the area of this wall. So I have to look at this area here. What would be this area? It would be equal to Ly, this part is Ly, this part is Lz, so Ly, Lz would be the area. So the total area here is Ly, Lz. It's the perpendicular area that the molecules hitting on the right hand side will see. So if I substitute that here, this is nkt over Ly Lz times Lx. This is just nkt divided by V, or I can write this as PV is equal to number of molecules Boltzmann constant times absolute temperature, or I can write this as P is equal to number density, number per volume, kT. So number density is capital N divided by V. So what I have obtained here is the equation of state for an ideal gas, or otherwise known as ideal gas law. It's the equation of state. It is an equation of state. So if I have basically new number of moles of gas, how do I calculate the number of moles knowing the total number of molecules? Total number of molecules divided by Avogadro's number gives me the number of moles. So for total number of molecules, I can use Avogadro's number times number of molecules. Avogadro's number is 6.02 10 to 23 molecules per mole. So I would have the average pressure times volume is, for N I'm using Na times number of moles kT, and number of moles Na K times T. So this is number of moles RT. PV equals nu RT, and AK is R, the universal gas constant. So this is our universal gas constant. It is the product of Avogadro's number with Boltzmann constant. Universal gas constant. So if you look at this relationship, PV is going to be a constant at constant temperature. If you plot P as a function of V at constant temperature, you would get a hyperbola. If you have a constant volume, P would be increasing with absolute temperature linearly at constant volume. And remember, this is the constant volume gas thermometer. And you can see here the PV curve. For a constant temperature, we have P is proportional to 1 over V, so it's the hyperbolic curve. On the other hand, if you increase the temperature, you see that these curves would shift up. So this is in the direction of temperature increase. And each of these curves where you see P is proportional to 1 over V relationship, they're basically called isotherms. So you have constant temperature, pressure, volume curves. And basically the equation of state I have obtained here, PV equals nKT or PV equals nu RT using the universal gas constant. This is valid for any gas in the ideal gas limit. So the equation of state that I have obtained here is valid for helium, monatomic gas, oxygen, polyatomic gas, methane, etc. if you have it dilute enough so that you can approximate it to be an ideal gas. So let's summarize what we said here. We had a quest to calculate the mean pressure of an ideal gas. We assume that this gas is inside a container with dimensions Lx, Ly, Lz. And I'm looking at the force exerted by a single molecule on the right wall. And I imagine that this force causes a displacement of this wall by an amount dLx. Therefore, the work done by the force, the dot product of force with the corresponding displacement, is Fr dLx. However, according to the first law of thermodynamics, this will result in a decrease in the energy. First law of thermodynamics, the infinitesimal limit we talked about. Remember, this is d bar q and d bar w because it's not a change in work. Basically, the work done by the gas d bar w is going to be minus d bar w here, so the energy will be decreasing. So the force is minus the derivative of energy with respect to Lx. And the mean force is just calculated using canonical distribution. And in the canonical distribution, I realized that the way I have written it, it could also be written as 1 over beta del ln partition function del Lx. And by substituting the partition function that I calculated previously in the previous section, I can find that the mean force exerted by one molecule is kT over Lx, and this result is independent of if it's a monatomic or polyatomic, because the contribution from intramolecular energy is independent of the dimensions, the derivative vanishes. And calculating the total mean force, I just multiply the mean force per molecule with the number of molecules n, and if I divide it by the perpendicular area Ly, Lz, I have pressure. And I find that pressure times volume is equal to number of molecules times thermal energy, kT, or Boltzmann constant times absolute temperature, T. If I replace number of molecules with number of moles times Avogadro's number, by looking at the constant, universal gas constant, which is defined as Avogadro's number times Boltzmann constant, I could also write this as P bar V is equal to number of moles times universal gas constant times the absolute temperature T. So PV is a constant at constant temperature. It's called an isotherm. Each such curve is called an isotherm. On the other hand, at constant volume, it's proportional to temperature. The isotherms keep shifting up. And the equation of state I have obtained for this case is valid for any ideal gas, whether it's polyatomic or monatomic, it doesn't matter.